Hello everyone, welcome to another video session. Previously I introduced some basic concepts from control. Now we're going to study a specific type of controllers called PID control and see what is a PID control and how we can use it to control the motion of the robot. And remember, the goal in control is to move the joint variables in order to get the robot into a desired position. Let's start with a simple example. Consider the case of pendulum. And we have studied its motion before we derived the dynamic equations of a pendulum. And we want to look at it again because it's a simple example of a one-link robot. You can see it as a robot with one link and one joint. So when you look at the pendulum, where are its equilibrium points? Or in other terms, if you let it move, where would it stay? It would essentially stay at one point after times go on, no matter where you move it to. When you release it, it will go to a specific state and remain there. This is called equilibrium. And where is the equilibrium for pendulum? The pendulum has two equilibriums. It could always fall down on the ground or it could stay upward. The upward position is the unstable equilibrium. When it's exactly upward, if you slightly touch it, it will fall down and come to the stable equilibrium, which would be on the ground. And the question is, okay, how can we change its equilibrium? In control terms, look at it as a robot with one link. How can you move it so it could go to your desired position, stay at the desired angle? How can we do that? Let's look at the equations for the pendulum. We derived this before. There's a second order differential equation for the pendulum that gives us the angle as a function of the torque that's applied to its base. If we look at it as a robot, the torque at the joint. And we can have inverse or forward dynamic equations for it. And now consider we wanted to move it to a specific theta, fix it at a specific angle, not its equilibrium. And we want to stay there. How can we do that? One good conceptual example is if we want to fix it at a specific point, let's assume that we add a spring and damper to it that will hold it at our desired angle. In this case, if the damper wants to move, if the pendulum wants to move, the spring and damper pushes it and bring it to that specific position. The spring applies a force proportional to its displacement, and a damper applies a force proportional to its velocity. If you don't know what damper is, you've already seen dampers in your if you have a bicycle or a car. There's a suspension mechanism that makes sure that the car is not vibrating much. For instance, when you go on a bumper, it makes sure that the car doesn't jump up and down really fast. A damper is like a spring. A spring basically absorbs the potential energy. Suddenly, as it moves fast, it tries to push it back down to where the spring initially is. A damper is similar, but it absorbs kinetic energy. It applies a force proportional to the velocity. So if something is moving too fast, the damper makes sure it moves slowly and potentially brings it to zero velocity. That's why spring and dampers are used a lot in suspension systems. Going back, assume we want to hold the pendulum using a spring and damper. If we attach them here, when the pendulum wants to move this way, the spring applies a force, bring it back to where we wanted it. And if it's going too fast in one direction, the damper also absorbs the velocity and makes sure it goes back to where it should be. So using a spring and damper, we can fix the pendulum at a specific angle where we want it. But these are like conceptual spring and damper. How can we do it in practice? In practice, we have a motor at one joint of the robot applying a torque. What if we ask this motor to behave like a spring and damper? For instance, like this. It has a spring term that applies a torque proportional to how much it's rotating and wants to bring it to our desired position. Let's call this theta d. So if it goes farther from theta d, it will apply a torque to bring it back. And we also have a damper. If it's moving fast away from that point, or it's not fixed with zero velocity at that point that we want it, it damps the velocity and makes sure it stays there. So if you ask the motor to behave like a spring and damper, it would be the same as adding a spring and damper to the pendulum, and it makes sure it stays where it should stay. This is the basic idea behind PID control. To add some spring and dampers, simulate effect of a spring and dampers at our inputs for the robot in order to make sure it stays where we want it to. Now, before we can understand exactly how this works, we have to look a bit closer at the equations. Consider again the equations for the damper, for the pendulum. And to make things simple, we assume it's a linearized equation. So previously we had sine of theta here. Assume that theta is small and it's equal, sine of theta is equal to theta. So this is a linearized version of the dynamic equations for the pendulum. And this is also a second order differential equation. We have theta double dot as a function of theta dot theta itself and the torque at the joint. We already know how to solve this equation. Let's look at the solution of it. From differential equations course, you probably know how to solve an equation like this, a second order differential equation. The answer to this equation will have a form like this. It's an exponential solution. And the way we solve this equation, we assume that we know it has this format and we have two unknown parameters. We put theta back into the equation and then calculate A and lambda. If we do that, we take derivative of theta and second derivative of theta, put it back in the equation. It should satisfy the equation, so it should be 0. Then A cancels out. A is a constant, doesn't matter. We get this equation for lambda. If this wants to be 0, lambda squared plus A times lambda plus B should be 0. And the solution for lambda is given by this equation. So if we wanted to find the solution of the second order differential equation, all we have to do is calculate the lambdas, put it back in the exponential term for theta. That would be our solution. Now, what does this lambda mean? What is this lambda term? This lambda term can have several possible solutions depending on what happens under this square root. In a case that A squared is bigger than 4 times B, we have a real number for lambda, and the solution will take this term. In a case that it's exactly 0, we have this solution. And if it's smaller than 0, under the square root, it would be a complex number, and the final solution will take a term like this. Cosine and sine would appear. If you don't remember why cosine and sine appears, if you remember this equation, and we have an exponential complex number is equal to a e power of alpha times cosine of beta t plus sine of beta t. So we have to expand the exponential term and we get this final solution. So for a second order differential equation, we have three possible solutions based on the parameters in the equation. These solutions actually have names. This is what we called overdamped. This is what we call critically damped. And this is what is called underdamped. Why? We can plot this and take a look at the answers. The solution of that second order differential equations can have three possible cases. One that is critically damped. This is critically damped. One is overdamped. And one is underdamped. From the equations, critically damped and overdamped had an exponential term and it would decay like an exponential function. Critically damped was when the number under square root was exactly zero. This is the fastest solution. Think of this as a pendulum. It has an angle theta. Critically damped means it just goes and falls into the equilibrium. The equilibrium being down here. Overdamped means it goes there but slower. Underdamped means it doesn't really get there. It gets there but oscillates a bit back and forth before becoming stable. So these are the three possible solutions based on the parameters of the equation. How much is the weight of the pendulum? What is the length of it? What happens mostly in the almost every time is that it's underdamped. It comes and oscillates. If there are massive frictions here, it would behave critically damped or overdamped. It just goes and stays at the equilibrium without oscillating. So these are the three possible solutions. Oscillating, remember that we have sine and cosine term for this scenario. Then it behaves like a sinusoidal signal, goes up and down. Critically damped goes really fast, overdamped slowly. So these are the three possible solutions for a second order differential equation like a pendulum. And for the most cases where there is underdamped, if you put the parameters in the equation, we can get a speed of decay using this term and the frequency of oscillation using this term. You can see it's a function of what is basically the friction, K, and what is the weight of the pendulum and length of it. So based on this, it will have this oscillatory behavior. Or if the friction is very large, it goes to critical or overdamped behavior. This is how a pendulum motion is. It's either one of these three cases. Think of now that we have added the spring and damper term, and we have a motor that simulates the spring and damper. The equations will turn into something like this. This was the dynamics of the pendulum, and this is now the motor torque that behaves like a spring and damper. Now let's look at the solution and see how it will turn out. If we again solve the equations, you will see that for the case of underdamped situation, we will again have our speed of decay as and the frequency of oscillations. So this would be the parameters for the equations after we add the spring and damper. You would see that now the constant for the damper and the constant for the spring show up in these terms. By looking at it, you can get an understanding of what that damper and a spring do. For instance, when we add damper, the damper can increase the speed of decay. If we increase KD, what does it mean? If you look at these figures again, when we increase the speed of decay, then the oscillations would become smaller and smaller by adding the damper, and potentially it could become critically damped and overdamped. So the pendulum goes slowly toward the equilibrium that we want and stays there. Also, when we add the proportional, the spring term, Kp affects the oscillation term as well. For instance, increasing the Kp would makes the oscillations worse, increases the complex part. Reducing it makes the oscillation smaller. So you can see that when we add a spring and damper, it can help to change the solution of the equations. That's what controller is doing. It's forcing the pendulum to behave in a way that we want. By playing with this KD and KP, we can force the solution to be something that we want. For instance, go directly to low underdamp with low oscillation, or even make it critically damped to behave in a way that we want to. Now, if we can even analyze the equations a bit more, we can consider the equations when we have a spring and damper term. Okay. And if we can write the equations by gathering all the terms for theta as this. Let's look at this equation and see what happens when the system is stable. Okay, now it went and became stable at the equilibrium, however it behaved, critically damped, overdamped, or underdamped. But when it's stable, what is the solution? When it's stable, all the thetas are zero, right? Theta dot, theta double dot, it's not moving. The theta itself, the angle that it stays at, would be like this. If we put all the derivatives of theta to zero, theta can be calculated using this equation. Theta desired is where we put the spring, where we wanted the spring to keep the pendulum. So you can see that theta reaches theta desired multiplied by a term. It doesn't exactly reach where we wanted it. It gets there but close to there. How can we make sure that theta gets to theta desired? If we increase Kp, a lot that goes toward infinity, this term would go toward 1. Then theta reaches theta desired. Now you can also see again what the controller does. Kd helped us improve the oscillations, make them lower and lower till potentially get critically damped. And Kp, if we increase it a lot, it makes theta equal to theta desired. So it gets it to exactly where we want it to. That's why the spring and damper works. It moves it slowly to exactly where we wanted it. And again, you can look at the final steady state angle of the pendulum when we put the derivatives equal to 0. This would be the final theta for the pendulum. As I said, it's not exactly where the theta desired should be. If we want to measure the error, subtract this from theta desired. This is our error. So the pendulum, we wanted it to go to theta desired, but it goes somewhere else. The difference in theta is given by this equation. So our error in moving the pendulum to where we want it is given by this equation. If you look at this equation, again, as I said, if we increase Kp toward infinity, this term will go to 0. So the error would be 0. Theta will become equal to theta desired. So by increasing the stiffness of the spring, we can make sure that the pendulum goes to where we wanted it. There is another way to do that. We don't really want to increase the stiffness of the spring a lot because first it's physically not possible, and previously from the solution of the equation you saw that increasing Kp a lot will make beta larger, the complex form, and makes the oscillation worse. It almost like as it's counteracting the damper. So we don't want very large stiffness for the spring. There is another way to handle this. We can add a third term, which we call integral term, to get rid of that steady state error. Previously, we assumed that the torque is like a spring, a damper. Now assume we have a third term, which is integral of the error multiplied by gain. This will force the pendulum to go to where we want. Basically, the torque will increase when the error is large. As time passes, this term will get larger and larger and makes sure that the pendulum goes to the desired theta. This second term is called integral term, and this is the basis of a PID controller. The first spring term is called proportional. The second term simulated the damper is called a derivative. And the last term is integral that helped us reduce that tiny error that was left. PID stands for proportional, integral, derivative. Derivative is like a damper, proportion is like adding a spring, integral term is just summation of the error throughout time to make sure we don't have any small error at the end. Again, this is what we call the PID controller. Three terms: proportional, which acts like a spring; second term, derivative, acts like a damper; third term, integral term. One thing that we have to notice, a spring and damper we could visualize how it behaves, but what about the integral term? Integral term can cause some problems. We usually try to avoid it as much as possible. If that steady state error that we had was small, we can even forget about it. What are the problems that it can cause? Basically, it's an integral term. So at initial point, assuming that the difference between the desired theta and theta is very large, then the integral keeps increasing throughout time and it won't decrease that much. This is called the wind-up effect. The integral terms keeps increasing, increasing, increasing. Suddenly a large torque is applied at the joints. And we don't want that. So that's why we keep the gain that's multiplied by it very small. Another way to handle this is that assume at the beginning we don't have an integral term, but at the end, when we're reaching the desired angle, you activate this term. You add this at the end to make sure the errors at the end are going to zero. Then you won't have to deal with a large integral term. There are ways to totally avoid integral term as well. As we saw that the steady state error, the error that we had was mostly because of this term, the gravity and the weight of the pendulum. What if we try to cancel it out in the equations? So instead of adding integral term, we have a spring or proportional term, we have a derivative term, and we add the exact equation for the mass of the pendulum that was in the error, or length of the pendulum times weight of it times gravity times theta. What happens? If you put back this into the equation, you would see that these two terms will cancel out. And then the steady state error would go to zero. So the theta that we want in the end would be exactly equal to the desired theta. This way we don't have to have the integral term and deal with some of its complexities. We don't need to increase Kp a lot, and we can get the desired angle as we want. What would be the challenge in this method? The challenge in this method is that we need to know exactly what is the mass of the pendulum. This is challenging. In reality, we don't have absolute values for these parameters, so still will give you a tiny bit of error because the mass that you're using is probably not exactly what the mass of the pendulum is. And as I said, this method needs a knowledge of the mass of the pendulum, and it could lead to small errors if the mass of the pendulum is not known, but still compared to a PID error, PID controller, when you have I term, it's sometimes considered better because having the integral term, as I said, adds some complexities, especially if at the beginning the error is too large. So we have the option to use this gravity compensation when we cancel out the gravity terms, or using an integral. Both of them work. It's up to us to pick which one for a specific type of controllers. So this was an introduction to PID. What is a PID controller? And to summarize, we saw that PID is basically like adding a spring, damper, and integral term to the robot with one link to force it to come where we want it to. And in practice, we can simulate this spring and damper at the joint level using the torque that's required to move the links. All we have to do is add those spring damper terms at the joints and move it. This was introduction to PID, but you might be a bit concerned, okay, how can we generalize it to a robot? This was one simple link with one joint. In the next video, I'll talk about how we can generalize this method and use it for robots.